AI moved fast again today, and if you blinked, you missed 3 headlines. This is Tech Roundup on the AI Verge, your daily dose of what actually matters in AI minus the hype. Let's get into it. Welcome to today's Tech Roundup. We are on a very specific mission today.
Yeah, we really need to separate the actual, tangible breakthroughs in physical AI from the purely theatrical noise.
Exactly, because if you look at our sources this week, there's a humanoid robot that allegedly just beat Usain Bolt's world speed record.
Right, which is just wild. And the company that built it, they just hit this staggering $50 billion valuation.
Which, sounds impressive on paper, but before you go welcoming our new robot track stars, you really need to see the other video we're tracking.
Oh, the track fail.
Yes, it's a different sprinting robot, and it completely loses control on an indoor track. Like, it completely fails to brake and literally snaps itself in half at the waist.
Yeah, that was a brutal watch.
It really was. So we're looking at the bleeding edge here.
Yeah.
The economics, the hardware failures, and critically, the back-end compute that makes any of this possible.
Because the gap between a heavily curated viral demo and a real-world functioning application has honestly never been wider.
Definitely. And look, if you want to cut through all this hype and just get the facts on what's actually happening in AI, hit subscribe to the AI Verge.
So let's start right at the intersection of, the money and the metal.
The Unitree IPO.
Exactly. Unitree's blockbuster IPO in Shanghai is kind of the macro story setting the tone for the entire industry right now.
And the numbers are just massive.
They're almost difficult to process.
Yeah.
On its debut, Unitree's stock soared 460% above its IPO price.
Wow.
Yeah, it closed at 845 yuan. So that single day of trading valued the company at around $50 billion.
Okay, let's put a pin in that 50 billion for a second.
You're skeptical.
Very, because we've seen hardware bubbles before, right? Think back to the early days of the EV boom, or I don't know, even the dot-com era, where literally any company with a dot-com in its name just saw its valuation skyrocket, regardless of revenue.
Right, the hype cycle.
Exactly. So my immediate question is this a reflection of actual commercial viability, or are we just looking at peak exuberance here?
It's a massive signal, I'll give you that. But it's not entirely ungrounded, I promise. You really have to look at the history of humanoid robotics to get why this is a big deal.
Okay, lay it out for me.
So for the last 20 years, building humanoids was basically just a really efficient way to set money on fire.
True.
You had these companies passing hands from Google to SoftBank to Hyundai, all because the R&D burn rate was just astronomical.
And the commercial applications were essentially zero, right?
Literally zero. Humanoids were restricted to university labs and massive corporate prestige projects.
Just showing off.
Exactly.
Yeah.
But Unitree is one of the very few companies in this space that is actually turning a profit.
Wait, really?
Yeah, mostly through their consumer-level robotic dogs, actually.
Oh, right. I've seen those.
Yeah, so a profitable robotics company achieving a $50 billion valuation, it proves the market believes the mass commercialization of physical AI is finally here. Founder Wang Jianxing's stake alone is now worth more than $11 billion. And he is out there in our sources explicitly calling this the industry's ChatGPT moment.
Yeah, see, I want to challenge that ChatGPT moment framing pretty hard.
How so?
Well, ChatGPT was a moment because hundreds of millions of people could immediately, log on, use it, and extract actual value from it on day one.
From their laptops, yeah.
Right. A robot that costs tens of thousands of dollars and requires highly specialized maintenance is a very, very different adoption curve.
That's a fair point.
And what actually triggered this massive valuation push right before their IPO, it wasn't a rollout of robots cleaning hospitals, it was a viral video.
The Superman robot.
Exactly. They pulled the curtain back on this new Superman robot just in time for the IPO.
Right, but from a pure engineering standpoint, the Superman robot is why the entire robotics community is buzzing right now.
Because it runs fast.
Well, the claim from our sources is that it hits 12.7 meters per second.
Which edges out Usain Bolt's record-setting speed, which was what, 12.4 meters per second?
Correct, 12.4. But look, speed is just one vector here. It can also reportedly clear a 2-meter standing vertical jump.
2 meters? From a standstill.
Well, a standstill, which beats the human standing high jump record, by the way.
Okay, that's undeniably cool, but again, what is the utility?
I know you're skeptical of the utility, but let me just geek out on the physics here for a second, because you cannot fake the mechanics required to do this.
Fair enough. Go ahead.
To achieve a 2-meter standing vertical jump, you are moving far beyond just clever software or traditional electric motors. You're talking about a fundamental leap in actuator technology.
Okay, break that down for me. What actually changes in the actuator to make that possible?
So traditional robot joints use geared electric motors. They're great for smooth, continuous rotation, like turning a wheel, right? But they are absolutely terrible for sudden explosive movements. If you try to force a geared motor to instantly launch a heavy metal chassis 2 meters into the air, the sheer kinetic force will literally strip the gears or just burn out the motor entirely.
Because it can't handle that kind of instant torque.
Exactly. To get this kind of instantaneous torque, engineers have had to design entirely new systems that basically mimic human tendons.
Tendons, like biological tendons.
Yeah. They use elastic energy storage. So think of specialized springs integrated directly into the joint. They can coil and release energy in milliseconds, almost like a grasshopper's leg.
Oh, wow. Okay, that makes sense.
And then add to that the battery requirements. You need power cells capable of massive instantaneous discharge rates without overheating.
Right, thermal management.
Yeah.
Yeah.
Solving those thermal dynamics and power delivery problems is just a massive engineering flex.
Look, I understand the mechanical achievement. I really do. It's an incredible piece of physics.
Right.
But my core practical question remains. Why?
You mean the business application?
Exactly. Does this actually matter for a business? Who really benefits from a robot that runs fast if it doesn't solve real-world problems?
Wow.
And keep in mind, these speed claims haven't been independently verified yet. We are just looking at a heavily curated viral demo.
Sure, it's a demo.
And in my experience, a sleek video of a robot sprinting in a straight line in a perfectly sterile environment does not translate to a robot that can, safely navigate a cluttered warehouse or step over a dropped wrench.
The sterile environment critique is entirely valid. The entropy of the real world is definitely the ultimate test for these things.
Right, because working alongside humans without becoming a massive liability is the actual goal, isn't it?
It is. But the argument for building an Olympic decathlon robot isn't that you're going to literally deploy it to run sprints in a warehouse.
And what is it?
It's the trickle-down theory of technology.
Like Formula One technology trickling down to commuter cars.
Yes, exactly that. Formula One cars push the absolute limits of aerodynamics and material science and thermal efficiency. Nobody needs a Honda Civic that goes 220 miles per hour.
I hope not.
Right. But the fuel injection systems and the composite materials they develop for the track eventually make your Civic safer and way more efficient.
Okay, I see where you're going.
Pushing the absolute limits of hardware, the speed, the torque, the balance required to sprint at 12.7 meters per second, it forces breakthroughs.
So the extreme edge cases solve the everyday problems.
Precisely. The same instantaneous torque and tendon-like actuator that allows a 2-meter jump is exactly what allows a factory robot to instantly catch its balance if it slips on an oil slick while carrying a 50-pound box. You train for the extreme edge cases to raise the baseline stability.
Okay, the logic holds, but I'm still looking at the immediate ROI.
Always look at the bottom line.
Someone has to. If these systems are going to actually integrate into the mainstream economy and, justify a $50 billion valuation, they need to be reliable today, not just athletic.
Right, practical utility.
Yes. Prioritizing basic household or industrial reliability over parlor tricks completely changes the engineering mandate, in my opinion.
Which actually brings us to how these machines are learning to operate in the real world.
The software side.
Right, because a robot doing a backflip is just relying on hard-coded physics. But a robot folding laundry, it actually has to understand its environment.
And that's moving fast.
Incredibly fast. Our sources are highlighting a massive update this week from a startup called Generalist AI. They're focusing on their GEN 1.5 model.
Okay.
And this is fundamentally shifting how robots acquire new skills.
Oh, this is the toddler learning breakthrough I was reading about.
Yes. They've unveiled a working model of one-shot robot learning.
Which means what exactly?
It means the GEN 1.5 model can pick up a brand new physical skill from a single 3 to 12-second video demo.
Just watching a video.
Literally. You show the robot a task once for a few seconds, and it understands what to do.
I mean, the numbers in the report definitely caught my eye. On its very first try, after watching that short video, the robot succeeds at the physical task 59% of the time.
And then, after just a few minutes of extra practice, the success rate jumps to 83%.
It literally mimics human developmental learning.
Exactly like a toddler.
Right. A toddler sees you stack a block. They try it. Their grip is slightly wrong. The block falls. They adjust. And 3 minutes later, they've completely mastered it.
And to understand why this is such a massive architectural shift, we need to look at how agonizingly difficult robot training used to be.
Because it wasn't just showing them a video before.
Oh, not at all. Historically, to teach a robotic arm to just pick up a strangely shaped object, you had to use reinforcement learning within a digital simulation, something like NVIDIA's Isaac Sim.
So purely virtual at first.
Yeah, you'd build a perfect digital replica of the object, and the AI would attempt to pick it up millions of times in a virtual environment, scoring points for success, losing points for failure.
Basically, the trial and error method just sped up digitally.
Right. But the massive problem there is what's called the sim-to-real gap.
The sim-to-real gap.
Yeah, because no matter how good your simulation is, it simply cannot perfectly replicate the slight friction of a dusty table or, the microscopic variations in a real-world motor's torque.
So when it moves to the physical world, it breaks down.
Exactly. When you transferred the AI from the simulation to the physical robot, it would often just fail in totally unpredictable ways.
Wow.
What Generalist AI is doing bypasses that massive bottleneck entirely. It's sparking fierce debates right now about physical general intelligence, or PGI.
Okay, let's define PGI for the listener really quick, because it essentially implies the AI isn't just programmed for one specific environment, but actually understands the underlying rules of the physical world, right?
Yeah, think of it like this. When you watch a cooking show, you instantly know how heavy the chef's knife is, how hard the carrot is, and how much force the chef is applying just by watching the pixels move on your screen.
Because we have an intuitive sense of physics.
Exactly. You have an internalized physics engine in your brain. PGI attempts to give that same intuition to a neural network.
So it knows things without being explicitly told.
Right. It doesn't need to be explicitly coded to know that dropping a glass shatters it, or that a heavy, smooth object requires a much firmer grip than a light, rough one.
That's fascinating.
By observing just a 3-second video, the model's vector embeddings actually map the 2D visual data into 3D spatial actions.
Which sounds like magic, honestly.
It extracts the physical parameters implicitly and applies its generalized understanding of physics to replicate the motion. It's the leap from rote memorization to actual physical intuition.
Okay, I want to ground this in reality, though.
Here comes the skeptic.
Always. Mapping 2D pixels to 3D actuator movements is brilliant, yes. But even the developers at Generalist AI explicitly state in our sources that these skills are developmental.
Very early stage, sure.
A 59% first-try success rate is a failing grade in an industrial setting.
Why, yes.
If a warehouse robot drops a package 41% of the time on its very first try, you are shutting down the entire assembly line. So I have to ask, is this genuinely useful right now, or is this just another really fascinating lab experiment?
Today, it's a lab experiment. I'll concede that.
Thank you.
But tomorrow, it is the absolute foundation for global deployment.
How so?
Because the single biggest bottleneck to scaling robotics is the deployment friction. You cannot mass deploy robots if every single unit requires a team of highly paid software engineers to hard-code its specific workflow for 3 weeks.
True, that's wildly inefficient.
Right. If a warehouse floor manager or a construction foreman or a nurse can literally teach a robot a new task just by physically demonstrating it for 10 seconds, you've completely democratized the technology.
So it's about accessibility.
One-shot learning is the key that unlocks the consumer market, period.
Okay. I will believe that when I see it happening reliably outside of a climate-controlled laboratory.
Fair.
Because right now, the hardware hitting the mainstream economy, the stuff actually driving revenue, isn't relying on generalized human-like AI.
No, it's highly specialized.
Exactly. The real commercial traction is happening with these highly specialized, incredibly affordable units. The supply chain has quietly matured, and the price points we're seeing in the reports this week represent a fundamental economic shift.
Oh, the plunging cost of hardware is easily the quietest revolution in tech right now.
Let's run through a rapid-fire roundup of this consumer-ready automation, starting with the home. We're tracking a San Francisco startup called Robotics.
Yeah, they're launching the Nori A3 this fall.
And this is a wheeled humanoid. So it has a wheeled base for mobility, but a humanoid upper torso with arms.
Right, kind of a hybrid.
It can lift 55 kilograms, it fetches items, and it can operate basic household tools. But the specification that actually matters here, The price tag.
It's insane.
It's $1,688.
That price point literally changes the entire conversation.
It completely shatters the barrier to entry. For years, any robot with this level of payload capacity and articulation cost anywhere from $60,000 to hundreds of thousands of dollars.
They were strictly industrial capital expenditures.
Exactly. But a $1,600 price point, that is the cost of a high-end laptop. It brings home automation out of the realm of experimental luxury and makes it accessible to the middle class.
And do you know how we got from $100,000 down to $1,600 in just a few years?
Supply chain efficiencies.
It's entirely due to the smartphone and EV supply chains.
Oh, interesting.
Yeah. 10 years ago, if you wanted a LiDAR sensor,
Yeah.
the laser radar robots used to map rooms,
Right.
it cost tens of thousands of dollars and looked like a spinning KFC bucket on top of a car.
Yeah.
But today, because of the massive scale of the automotive industry, solid-state LiDAR sensors are the size of a postage stamp and cost a few dollars.
That's a huge drop.
Same goes for the IMUs, the inertial measurement units that keep the robot balanced. The gyroscopes in your smartphone drove that cost down to absolute pennies.
So they're just repurposing existing cheap tech.
Nor Robotics is just packaging commoditized, incredibly cheap components with modern AI.
And they're pairing it with a software ecosystem, too. The sources say the Nori A3 comes with an app store where owners can upload and share the physical skills they've taught their robot.
The network effects of an embodied app store are wild to think about.
How do you mean?
Well, you buy the robot, you bring it home, and suddenly it knows how to perfectly fold a specific brand of laundry because someone 3,000 miles away taught their robot how to do it, and the data was aggregated.
Okay, I remain highly skeptical about a $1,600 machine navigating a chaotic living room with, children, pets, and changing lighting conditions.
It won't be perfect on day one.
But the economic threshold has undeniably been crossed. And we're seeing this same aggressive cost-cutting and automation hitting retail right now.
Oh, the JD.com story.
Yes. Look at JD.com's new coffee shop in Beijing.
This is a masterclass in specialized high-throughput automation.
Completely.
It's a fully automated 24-hour coffee shop running entirely on a single robotic system.
A customer just taps their order on a touchscreen.
Right. And the system grinds the beans, brews the espresso, steams the milk, and delivers the finished drink through a secure cubby. Zero human intervention.
And the volume it handles is the critical metric here. Our sources note it served 202 drinks in a single session, taking under 30 seconds per cup.
That's fast.
Think about the unit economics of a retail location when you completely eliminate the variability of human labor.
It's a game changer for retail.
A machine doesn't need a break, it doesn't get overwhelmed during the 8:00 a.m. rush, and it maintains a perfect, identical 30-second cadence per cup, indefinitely.
It turns a chaotic retail environment into a predictable manufacturing line.
Exactly.
And this embodiment of AI isn't stopping at retail or home care either. It's bleeding directly into our personal workspaces.
Oh, this was bizarre.
The most bizarre yet compelling update this week comes from Autonomous Labs. They just launched an open source product called Lamp.
And it is quite literally just a desk lamp.
It looks like a standard architectural desk lamp, yeah. But it's priced at $499, and it packs a camera in its head, 5 motors in its articulated joints, and a microphone array and speakers built into the base.
So it's fully interactive.
It can listen, talk, and move autonomously.
And because it's open source, developers are already turning it into an embodied desktop assistant.
Right, it tracks you.
Yeah, it can track your posture, adjust the lighting based on the ambient glare on your monitor, and interact with you verbally.
It gives a physical presence to the chatbots we've been confined to using through a keyboard.
It's accessible, affordable, and hyper-specialized.
But, and I have to emphasize this before we crown this era as the frictionless utopia of cheap consumer robots, we desperately need a reality check.
My favorite kind of check.
Because the fundamental physics of these machines are still causing catastrophic, highly public failures.
Which brings us back to the World Humanoid Robot Games.
Yes.
This is an event happening right now in Beijing, featuring 2,056 robots. It is designed to be a massive showcase of scale and capability.
Right.
But the singular viral moment to emerge from this massive event is an absolute disaster.
We touched on it in the opening. It is a really brutal piece of video.
It's a sprinting robot running a training heat on an indoor track. It accelerates smoothly, it gets up to a really high speed, and then it crosses the finish line and completely loses control.
It just doesn't stop.
It fails to initiate any kind of braking sequence whatsoever. It continues at full speed and slams into a padded barrier with so much force that the entire machine violently snaps in half at the waist.
Ouch.
The top half folds entirely over the bottom half.
From a purely visual standpoint, it's almost comical.
It is.
But from an engineering standpoint, it brilliantly exposes the exact bottleneck in current humanoid design.
Right. It proves that basic physical guardrails like balance, deceleration, and braking are still fundamentally unsolved problems.
Everyone is focused on acceleration right now.
Exactly. It is relatively easy to program a robot to put one foot in front of the other and increase speed. It is a vastly more complex physics problem to manage and dissipate the kinetic energy required to stop safely.
Let's actually talk about the physics of braking for a second, because it highlights why humans are still vastly superior machines.
I'm listening.
So kinetic energy scales with the square velocity.
Okay.
When that robot is sprinting, it is carrying a massive amount of forward momentum. Now, when a human sprinter crosses the finish line, they don't just lock their joints.
Obviously not.
Right? Their brain makes thousands of subconscious micro-adjustments in milliseconds. We lean back to shift our center of gravity, we change our foot strike pattern from the ball of foot to the heel, and our muscles perform eccentric contractions, which is lengthening while under tension to absorb the shock.
We intuitively act as our own shock absorbers.
Exactly. Translating that intuitive kinetic dampening into code and then executing it through mechanical actuators without stripping the gears, overheating the motors, or losing balance, it is incredibly difficult.
So the energy has to go somewhere.
Yes. When a robot tries to stop suddenly, the kinetic force has to go somewhere. If the software doesn't perfectly manage the deceleration sequence, that energy travels straight into the weakest structural point of the chassis.
In this case, the waist joint.
Yep. The robot snapping in half is a blunt, violent reminder that we are still in the very early, messy days of hardware testing.
Which perfectly illustrates my core argument. What is the practical utility of a robot that runs 12.7 meters per second if it cannot figure out how to stop without literally destroying itself?
It's a work in progress.
I would much rather see capital investment flowing into boring, reliable machines that can operate safely for a decade rather than a humanoid that can sprint for 10 seconds and then disintegrates.
And to be fair to the industry, massive capital is flowing into pragmatic automation right now.
It is.
Yeah, the sprinting humanoids get all the viral views on social media, but the real economic tectonic shifts are happening in the background.
Like what?
Look at SoftBank's latest move. They just poured $200 million into a Swiss startup called Gravis Robotics.
And Gravis isn't building fragile humanoids.
Nope.
Their entire business model is turning existing massive construction machinery into autonomous robots.
Which is brilliant.
They're taking the heavy excavators and bulldozers we already have, installing sensor suites, and giving them a digital brain to operate autonomously on a job site.
It's highly pragmatic, and we are seeing the exact same push in logistics. Uber Eats and Zipline just announced a massive expansion of their drone delivery partnership.
I saw that. Their stated target is incredibly aggressive.
Very. They want to hit 1 million daily drone deliveries by 2029, with the first major rollouts happening later this year.
1 million deliveries a day fundamentally alters local logistics.
Oh, yeah.
It changes municipal traffic patterns, urban noise levels, and it relies entirely on regulatory approval, which is slowly clearing the way.
Like the Waymo news.
Exactly. Waymo just secured approval from the California Public Utilities Commission, the CPUC, to expand their autonomous robotaxi service across the entire Bay Area and Los Angeles, while simultaneously rolling out in Sacramento and San Diego.
It's happening.
We are actively watching autonomous vehicles transition from geofenced pilot programs into ubiquitous public transit infrastructure.
But I'll tell you, the most grounded example of practical automation, literally grounded, is happening in Colorado right now.
The 3D printed houses.
Yes. There is a 55-acre development in Salida called Cleora. They are building 106 homes, and more than 65 of them are being constructed by 3D printing robots.
And this isn't a speculative render on a website.
No, real houses.
7 of these homes are already finished, certified, and sold. They have two massive autonomous printing systems currently working the site, extruding concrete layer by layer.
That's wild to watch.
This is one of the largest real-world tests to date of whether robotic construction can scale beyond gimmicky showcase homes and actually address real housing shortages.
A gantry robot slowly printing concrete walls doesn't generate the same hype as a humanoid backflip.
Not at all.
But it is infinitely more important to the mainstream economy.
Completely agree. But here is the connective tissue for this entire deep dive today.
The compute?
Yes. Whether we're talking about a $1,600 home robot fetching laundry, a massive 3D printer building a house in Colorado, a fleet of autonomous Waymo taxis navigating Los Angeles, or a robot snapping in half on a track, they all share one critical, invisible vulnerability.
The back-end intelligence.
Right. None of these physical machines operate without massive, continuous streams of data and inference driving their decisions.
And that intelligence back-end is getting painfully expensive. Which actually brings us to the second half of our briefing today. We need to tackle the grim reality of scaling these operations and provide you with a highly actionable productivity workflow to bypass the looming bottleneck.
Because whether you're a developer tinkering with a $500 open-source desk lamp or an enterprise executive trying to deploy a fleet of autonomous customer service agents, relying on massive generic cloud models is rapidly becoming a financial liability.
A huge one.
Our sources highlight a crucial macro statistic from Gartner this week that should make literally anyone building with AI pause.
Yeah. Gartner estimates that inference costs are going to grow fivefold, a 500% spike by 2028.
Okay, let's break down exactly why that is happening, because you really have to understand the difference between training and inference.
It's a key distinction.
Training the AI model is a massive upfront capital expenditure. It's basically buying the taxi. Inference, on the other hand, is the operational cost. Every single time you ask the model a question and it generates a response, you are paying for the compute.
It's paying the taxi meter.
Exactly.
And when we first started using large language models, the workflow was incredibly simple. Prompt and response. You type a question, it generates an answer, one input, one output.
The taxi drives one block and stops.
Right. That is a predictable, manageable amount of compute. But the entire industry is shifting toward agentic workflows right now.
And agents do not operate on prompt and response.
Exactly. Agents execute complex tasks autonomously. If you tell an agent to, quote, research our competitors and write a report, it breaks that massive goal down into dozens of intermediate steps.
Behind the scenes.
Yes. It queries a database, reads the results, evaluates if the information is actually useful, loops back if it hit a dead end, drafts a summary, critiques its own summary, and edits it.
Just constantly looping.
And every single one of those internal steps requires an inference call. The taxi is literally circling the city for hours. An agent trying to solve a single problem might consume hundreds of times more tokens than a simple chat interaction. So when you scale that up to enterprise levels, thousands of agents running continuously, that 5x cost spike is practically guaranteed.
So we are staring at an unsustainable paradigm. The hardware is getting cheaper, but the digital brains required to run them are skyrocketing in price.
Yep.
If a company relies entirely on generic APIs from massive cloud providers for every micro decision their agents make, they're going to bankrupt themselves on inference costs alone.
Which is exactly why the smartest players in the industry are abandoning the generic cloud models for specialized, vertically integrated infrastructure.
Okay, let's talk about that.
Our sources highlight a company called Crusoe as a prime example of this shift. They are trying to make deployment significantly cheaper and faster by owning the entire stack.
Vertical integration, which means they aren't renting servers from someone else who's renting power from a utility.
Right. Crusoe's pitch is that they manage everything from the actual energy generation to the data center cooling to the bare metal cloud infrastructure.
Michael Yen-Chi Ho, their director of technical product marketing, noted in the sources that cutting out the middleman at every layer allows them to offer high-performance inference at a fraction of the cost.
But more importantly, it allows them to optimize for speed.
Speed is everything.
They utilize a technology called memory alloy, claiming it delivers a 9.9 times faster time to first token and 5 times greater throughput compared to standard setups like VLLM when running massive open source models.
Let's pause on time to first token because that is the only metric that matters for user experience.
It really is.
When you ask an AI a question, or when a robot is processing visual data to make a split-second physical decision, The agonizing delay before the first piece of generated data comes back is the time to first token.
And we all hate that delay.
Achieving a 9.9 times speedup is the difference between a natural voice conversation with an AI and an awkward, laggy phone call.
Or for a robot, it's the difference between catching a falling glass and just watching it shatter on the floor.
Exactly. So the overriding goal for developers and businesses right now is to bypass the latency and the exorbitant costs of generic cloud models.
Which leads us to the actionable workflow for this weekend.
Yes. Let's get into the weeds here. If you are leading a small team or building a product and you want to escape this looming 5x cost spike, what exactly is the setup?
Well, you need 3 specific components to bypass the generic cloud trap.
Okay, what are they?
First, you need a top-tier open source model. Second, a highly specific custom dataset relevant to your actual work. And third, a serverless fine-tuning platform that handles the heavy lifting of the infrastructure.
Let's walk through the mechanics of this workflow step by step for the listener.
Step 1. Skip provisioning your own infrastructure entirely. The days of manually configuring Kubernetes clusters, fighting over GPU availability, and managing memory allocation are just over. You want to use a managed, serverless intelligence service.
Because bare metal provisioning is an operational nightmare for a small team.
Oh, it's awful.
It takes weeks of engineering time to set up. It is incredibly complex to secure. And if you misconfigure the auto-scaling, you are burning cash on idle compute when the model isn't even being used.
Exactly. Serverless means you only pay for the exact compute you consume, and the platform handles the scaling automatically.
Okay, step 2.
Step 2, data ingestion. Take your custom data set, maybe it's your company's internal customer service transcripts, a specific archive of research PDFs, or historical supply chain logs, and upload it to the serverless platform.
And step 3 is selecting the open source model. And the key here is not to over-index.
Yes, please don't over-index.
You do not need a monolithic trillion-parameter model to analyze internal sales data. A smaller, highly focused open source model will be exponentially faster, cheaper, and often more accurate for specific tasks because it isn't carrying the dead weight of knowing how to write Shakespearean sonnets.
Right. And step 4 is where the real performance optimization happens. Step 4 is utilizing built-in high-performance tokenizers to optimize the serving and throughput.
Like what?
Our sources specifically highlight open source contributions like fast tokens.
Okay, explain tokenization simply, because this is where a lot of people get lost in the jargon.
Sure. Language models do not read words. They read numbers. A tokenizer is the engine that chops human text up into chunks, sometimes full words, sometimes just syllables, and assigns a numerical ID to each chunk.
Okay, makes sense.
Historically, tokenization was a CPU-bound bottleneck. The CPU would chop the text up and then send the numbers to the GPU for the heavy mathematical lifting.
So the CPU is too slow.
Yeah, as GPUs got exponentially faster, the CPU couldn't tokenize the text fast enough to keep the GPU fed. Fast tokens and similar optimizations integrated into mainstream serving platforms like VLM and SGLang fundamentally streamline this pipeline, bypassing the bottleneck and radically improving how many tokens the model can process per second.
So let's look at a practical example use case. An engineering team could take an afternoon over the weekend, gather a clean data set of thousands of resolved IT support tickets, upload it to a serverless fine-tuning platform, select an efficient open source model, and train a localized, highly specialized IT agent.
Yep.
And because they are using optimized infrastructure with fast tokens or memory alloy, this localized model responds almost 10 times faster than querying a generic external API and costs a fraction of the price per inference call.
That is exactly the workflow. You achieve immediate production readiness, customized to your proprietary data, without managing a single server or writing a line of infrastructure code.
All right, I have to step in with a skeptic check here.
I knew it was coming.
What is the catch here? Because fine-tuning in an afternoon sounds like an incredible piece of marketing speak until you realize that most internal data sets are a complete disaster.
Yeah, data hygiene is tough.
They're full of unstructured PDFs, conflicting legacy information, duplicated files, and outdated policies. Doesn't utilizing these serverless deployments still require a massive amount of operational oversight just to ensure the AI isn't learning from garbage data?
You are absolutely right that data hygiene is paramount. A fine-tuned model is only as intelligent as the data you feed it. Garbage in, garbage out.
Always.
However, the catch isn't in the infrastructure anymore. That is the entire paradigm shift of this workflow. The point of a managed serverless deployment is to completely offload the operational hassle of the hardware.
So you are saying it frees up your engineering hours to actually clean the data?
Exactly. Instead of your DevOps team spending 3 weeks configuring clusters, managing drivers, and optimizing GPU memory allocation, they spend that time curating the data set, scrubbing the bad PDFs, and defining strict latency and compliance requirements.
Ah, okay.
You focus entirely on the model behavior and the data quality. You let the platform abstract away the hardware.
Okay, that makes practical sense. Stop fighting the hardware, start refining the knowledge base. The technology is finally getting out of its own way.
It really is.
Which makes this the perfect weekend challenge for you.
The challenge is straightforward. Take 30 to 60 minutes this weekend. Find a clean, small data set that you actually use for work or research.
It doesn't have to be massive.
Right, just a few dozen high-quality documents, a clean spreadsheet, or a set of standard operating procedures. Upload it to a serverless fine-tuning platform, select an open-source model, and run a basic test before Monday.
It is all about breaking the habit of relying entirely on generic chat interfaces for your workflows.
Okay.
Get your hands dirty with the localized infrastructure that is actually going to power the next wave of enterprise AI.
And hey, if you end up trying that fine-tuning workflow this weekend, make sure you subscribe to the AI Verge so you don't miss our next breakdown of the tools that actually matter.
Absolutely. Let's bring this all together.
Yeah, let's recap.
The biggest macro takeaway from everything we've tracked this week is a story of extreme contrasts.
Very true.
The robotics industry is flush with unprecedented cash. We are looking at $50 billion valuations, IPOs popping 460%, and actuator technology breaking world speed records.
But on the practical side, the basic physics of braking, kinetic dampening, and real-world utility are still frantically playing catch-up to all that hype.
And the one critical thing you need to watch moving forward is the underlying operational cost of all this ambition.
With inference costs projected to spike 5-fold by 2028 due to complex agentic workflows, the future doesn't belong to the companies just building the flashiest, most massive models.
Right, it belongs to the companies shifting toward vertically integrated, highly optimized, open-source infrastructure.
Which brings us back to your action item. Stop just reading about these models and get your hands dirty with serverless fine-tuning this weekend. Test the latency, look at the throughput, and see the difference a specialized model makes on your own data.
See you next time.